Today we want to talk about acceleration and free fall and the letter G. Sesame Street is brought to you today by the letter G. Near the Earth, not way out in outer space, but near the Earth, objects in a vacuum. What do I mean by a vacuum? No air resistance, because air resistance does change things. But in a vacuum, where there's no air, they all fall to the Earth with the same acceleration, regardless of their mass. Galileo was one of the first people to realize this. Yes, a feather will fall, will accelerate at exactly the same rate as a bowling ball. Put your pencils down, look up. So, a feather and a bowling ball in a vacuum pierce will fall at exactly the same acceleration. On the Earth, we're not going to be in a vacuum, but let's pretend from now on that any of the projectiles that we're talking about, anytime we're dropping something, I'm talking about this. It's pretty aerodynamic, it's got a lot of mass. Air resistance is not going to play a big role. This would fall and barely notice air resistance at all. That's something was vibrating there. Okay. What's pulling them down? The answer is much more complicated than you realize. There's a simple explanation why: gravity. But you can go down a rabbit hole of Einsteinian general relativity physics and actually say, no, gravity doesn't exist. There's another way to think about it. For now, this year, for a while, we're going to stay at the top level. We're going to say gravity's pulling them down. What's gravity? Gravity is that force that masses exert, big masses like planets, pulling things towards them. And because it's G for gravity, we use a lowercase letter g to represent the strength of the Earth's gravitational field. On Earth, G equals, you actually learned this in Science 10 last year. Does anybody remember the acceleration due to gravity? Negative 9.8 meters per second squared. I put it on your formula sheet, I think. I'm pretty sure I did there. You'll memorize this one because you get sick of looking it up. In fact, this is how I know someone hasn't done the homework. If I say to them, what's G? And they haven't done the homework at all. You'll memorize this one without even trying. In fact, Alec, people often talk about G forces. They shouldn't. They should be talking about G accelerations, because it's an acceleration, not a force. You're accelerating at 1G or at 2Gs or at 3Gs. So I'll always just say Gs. I don't think you'll ever catch me saying G forces, because it's not a force, but saying G acceleration, that's a lot of writing and long work. So I'll just say, how many Gs? 1G is exactly 9.8. Negative if you want to add a direction, but 9.8. Or really, what's a nice round number really close to 9.8 if you're trying to do math in your head? Yeah. 2 Gs is exactly 9.8 times 2. 19.6. Or approximately 20. 3 Gs is 9.8 times 3. Or approximately 30. Sorry? Oh, 6 Gs. What did I say? 3 Gs. 6 Gs. Yeah, here we're going. Well, approximately 60. That I can do in my head. 6 times 9.8? Well, 6 times 10 would be 60. 0.2 times 6 is 1.2. So it's going to be 60 take away 1.2. I bet you're seeing 58.8 on your calculator. I can do math in my head. When I have a calculator, I use 9.8. When I'm standing in line at Disneyland or Playland and I want to calculate how fast I'm going to be going at the bottom of the roller coaster, and of course, why would you not be calculating that when you're standing in line? Well, then I'll use 10, and I know I'm pretty close. I can't be... By the end of the year, you also will be able to stand in line at amusement park rides and calculate some numbers ahead of time. It only adds to the experience. So, outside of a vacuum, Air resistance can really lower G. So a piece of paper, for example, has massive air resistance. That is not accelerating at 9.8 meters per second squared down. We're going to ignore air resistance almost all the time. We won't always. We will eventually have enough physics, Gracie, where we can be more accurate and say, hey, let's include air resistance too. But that's going to take us a while to get there. Human beings can survive 25 Gs without, in most situations, without dying, although anything over 10 Gs will break ribs, break bones. If you're experiencing 10 Gs, that's about the equivalent of 10 of you dogpiling on yourself. If you're experiencing 25 Gs, that's about the equivalent of 25 of you dogpiling on yourself. So yeah, 25 people piled on top of me, that wouldn't be comfortable. 10 people piled on top of me, yeah, that might break a bone. So if you're looking for a rough frame of reference. At Playland, the ride with the highest Gs is approximately 4.5. Which ride? I think I mentioned it the other day, but if you've forgotten, sign up for Physics 12 next year. In Physics 12, we do a field trip to Playland in May, and we find out. We go on the rides with accelerometers and do some calculations. And it only adds to the experience. Turn the page. How do we know how much human beings, how many Gs human beings can survive? Some of it is by looking at data after car accidents and other accidents, but some of it is actual in-lab testing. In particular, some of our data came from an Air Force doctor named John Stapp. He was in charge of the crew in the Air Force back in the 1950s that was responsible for figuring out how ejection seats for pilots could work. We did not know if it was even possible for a pilot to eject at such a high speed and survive. And so the question was, well, do we even put in an ejection seat? Because if it's going to kill them, maybe it's better that we just force them to try and land the plane. That might increase their odds of survival. Even if the plane is totally busted, if ejecting is going to kill them every time, that at least, they might survive the plane crash. So we had to do some tests. So Air Force Dr. John Stapp was involved in designing and testing ejection seats for airfighter pilots. How do you test that? He rode a rocket sled that ran on a special track, and he was subjected to 15 Gs for 0.6 seconds and a peak of 22 Gs during a 1954 rocket sled test. So this photo here, he is experiencing around 22 Gs. That's not his maximum. His rocket sled was traveling at 0.9 times the speed of sound, or Mach 0.9. Mach 1 is exactly the speed of sound. Mach 2 is twice the speed of sound. You may have heard those terms. This is around 300 meters per second. If he came to a stop in 0.68 seconds, how many Gs did Dr. Stapp experience? What's this question asking me to find? Acceleration. What's that 300? Which one? Look up, look up, look up. Which one? Yeah. See the English physics word that tells me? Write that down. VI is 300. What's VF? What's 0.68? I'm looking for an equation that has A, VI, VF, and T in it. Mm-hmm.
A equals VF minus VI over T.
I was going to say, Weil, can you get the A by itself? But you already did it for me. Do you see it? So he's reached the point, and you're free to do this now, where he can look at the equation, which is VF equals VI plus AT, and Weil said, I can rewrite it in my head. Isn't it kind of a nerdy little feeling of accomplishment? Booyah, right? He said it's going to be the VF stays where it is. I would minus the VI, and I would divide by T. I'm really going to push all of you peers to try and get to that spot. It's a nice place to get to. It's lazier. It's actually easier once you get there. You'll find you make less mistakes with letters than you do with numbers. I'll go 2 times 3 equals 5 all the time. I still make that mistake. 2 times 3 is 6. But I'll never go A times B. 8 times B is 8 times B. I don't have any other option. All right. 0 takeaway, 300 divided by 0.68. By the way, if he's coming to a stop, is he slowing down or speeding up? I'm going to ask you the same question. I'm just going to phrase it differently. Am I expecting a negative or a positive acceleration here? Okay. Zero minus 300 divided by 0.68. Negative 441.2. We'll carry some extra sig figs with this because it's impressive. Negative 441, what did I say? 441.2? Now that's meters per second squared. How do I convert that to G's? To convert an acceleration in meters per second squared into G's, you divide by 9.8. You find out how many 9.8s fit in there. So now I'm going to say G equals, negative 441.2 divided by 9.8. I'm not going to divide by negative 9.8. The negative comes from the fact that gravity acts down, but here we're not talking about gravity. We just want to compare it to how many G's so that we have some kind of frame of reference. So I'm going to take this, divide by 9.8, and he pulled off and survived that gets a few exclamation points.
Can these be negative, or are they just...
It's a great question. Okay? Because he's slowing down, we would call these negative G's. He was even fussier. He said if you're going forwards and your eyeballs feel like they're going to pop out, he said, I'm going to call that positive G's. If I'm going backwards and it feels like my eyeballs are getting pushed in, typically in a car crash situation, we call that negative G's. So he also did experiments riding forwards and riding backwards. It turns out if you take the impact going backwards, it's much easier on your system, which is why in U.S. military planes, transport planes, only the pilot seats face forward, all the passenger seats face backwards. Why don't they do that on passenger planes like 747s? Because too many people would throw up and get sick, and it costs more to clean up the vomit than it does to pay off the insurance when people die. Sorry, it's a business world out there. So, pardon me? Airsick. Try driving for a while facing the back. You'll find probably half the people start throwing up after a while because your body isn't used to moving backwards and looking behind you. Yeah. Oh, yeah. Sorry. In another test, so 45 Gs. This guy is one of my nerd heroes, by the way. He also exposed his face to 940 km/h winds in another test because it wasn't just the ejection and the speed. He was wondering what will happen if I'm still in the plane, but the window shatters. What if the plane is flyable, but bullets have broken the cockpit, the windshield? Now what? Can I still fly? Turns out you can. How do we know? He tried it on the rocket sled. Put your pencils down. Where does that 9.8 come from? We are going to try and measure it ourselves for the remainder of class. Okay? Pause the video.